A lesson on moments then. It's the first of a series of 2 lessons really on machines. So moments is where we're starting. You need to be clear on the difference between moments and momentum. Very different things. We'll talk about momentum later. Just hold that thought. So the moment of a force is the turning effect of the force. So if you think about a door handle, you apply a force here and the door handle tends to turn, and the idea is to make the axle here turn, which is connected to the catch that sticks into the door frame to pull that back. So there you have a turning effect of the force. Now you would know that if you try to turn the door handle here rather than here, it's much harder. So to get the same turning effect, bringing it closer to the axle here, you need a larger force. So the size of the moment is the size of the force times the perpendicular, I'll come back to that in a moment, distance of the line of action, I'll come back to that as well, of the force from the pivot. So what do I mean by perpendicular and what do I mean by line of action? Well, line of action is really easy because here's the force and there's the line along which the force is acting straight down here. Perpendicular, well, this means at right angles to. It's an old word for at right angles. So the line of action is here. The right angle distance, well, that's there, right? So the moment would be F times D. Now if we think about your seesaw example, if we have child 1 sitting here, and let's say child 1 has a weight of a mass of 40 kilograms, and if we just do this nice and roughly, use G as 10, the weight would be 400 newtons. And let's say that child is 2 meters from the center of the seesaw. So I come along and I'm going to balance the child. Well, if I was to sit here, which is also 2 meters from the pivot, being heavier, that's going to mean that I'm going to bring the whole thing down here, right? And the child is going to go up. So to balance it, I'd have to sit nearer. My turning effect over here is too great, so I have to move in a bit. So let's say that I have a mass of 80 kilograms, so roughly speaking that's 800 newtons here. Then you can probably see that if I double the size of the force to get the same turning effect, I would have to cut the distance in 2. So you can see here that my 800 newtons is trying to turn the whole thing this way, anti-clockwise. Whereas the 40 Newton is trying to turn it clockwise. And if the moment of this and the moment of this are the same, then it's not going to turn. So we have a principle of moments which says for a body, an object, to be in equilibrium, here's another key term for you. You've had moment, you've had perpendicular, you've had line of action, you've had pivot, now you have equilibrium. For a system to be in equilibrium, the sum of the clockwise moments about any point, you usually pick the pivot, but you don't have to, equals the sum of the anti-clockwise moments about the same point. So, what do we mean by equilibrium? Well, equilibrium means not accelerating. You've come across this with forces before. Now, it might be that it isn't moving, but it doesn't have to be stationary. It's just not accelerating. So, acceleration is the rate of change of velocity, which means if it's not accelerating, there is no change in the velocity. And note I'm saying velocity, not speed, but velocity. So, you have, for a body to be in equilibrium, the sum of the clockwise moments about any point equal to the sum of the anti-clockwise moments about the same point. So there are 5 aspects to that definition, that statement of the principle of moments. So we have said what a moment is the turning effect of a force. We've said how to calculate the moment, the size of the force times the perpendicular distance of the line of action from the pivot. So you've had perpendicular line of action, pivot and moment as key terms. We've looked at an example of that on the seesaw, as well as the door handle up here. We've introduced the principle of moments, which you need to be able to quote. And I've talked about the sum of the clockwise and the sum of the anti-clockwise. So let's take an example where we have more than one turning effect in each direction. So let's say we have a big long steel bar, and what we're trying to do is to shift a great big rock in the garden. I don't have any imagination, so my rock is very geometric. So let's say the distance between here and here is 10 centimeters. And this is the force exerted by the load, this big rock in the garden. Now let's say we have a very long steel bar. Let's say that this is maybe, 3 meters long. And let's say your big brother or someone is leaning on this end. Let's say you've got an adult leaning on this end. So the adult's force is 3 meters from the pivot, but it's still not enough. The turning effect, A times 3, is not enough. So you come along and say, well, I'll jump on here. I'll come on at 2 meters from the pivot. So now you've got your big brother or whoever, the adult, here, trying to turn it clockwise, and you've got you here, trying to turn it clockwise. And then your little brother or sister comes along and thinks this is a great game, and they decide what they're going to do is to pull up on the beam. So you and your big brother or whoever are pushing down for all you're worth, trying to shift the load, and this little person comes along, thinks it's a great game, and starts pulling against you. So our clockwise moments, well, we've got the force due to A times the perpendicular distance of their line of action from the pivot. We've also got the force that you were producing times the perpendicular distance of your line of action from the pivot. And on the anti-clockwise side, well, we've got the load times 0.1, but we've also got the rather unhelpful little brother or sister or whoever, and let's say they're in there at 1 meter. So you can see that you can have more than one force. And it's not just about left-hand side, right-hand side of the pivot, because the forces could be up or down. They could be in any direction really, but they'll only be up or down for you. So it's not about left and right of the pivot, it's about the direction that the force is trying to turn the beam. So B is trying to turn it anti-clockwise, just like the load is trying to turn it anti-clockwise, whereas Y and A are trying to turn it clockwise.